Hello, I am Parker Brown, and here is my final project for the class. I did a project on cryptographic algorithms, so I'm going to go a little fast. My motivations, I always liked cryptography as a kid. I liked doing riddles and little codes and stuff, and I was really excited about creating my own cipher. So what I did, I started off, I went online, researched some popular algorithms, started with some of the easy stuff, then moved on to some of the more modern stuff like RSA and AES, and then I made my own unique cipher. So the Caesar cipher and Vigenère cipher, they're both linguistics based. They break up a text into numbers, and then they add different numbers to them. So Caesar adds the same number to everybody. Vigenère has a rolling key that it adds. So if we look here, we can go to Caesar. So it asks us do we want to encrypt? We say, hello, what is your shift? One. And you can see here that the things get shifted one up and then they get shifted back. And then we can also attack. And this just goes through all of the possible combinations. And we can see that one looks like English while the rest doesn't. Um, then next we have the Vigenère, which is the one that rolls around like a key. And for this one, I have the Gettysburg Address loaded up, and you'll see why. Our key can be Tom. So yeah, this rolls around, and it adds the corresponding number value of Tom to all of them, and then to encrypt, and then it subtracts it to decrypt, and then we can also do an attack, which is why I picked such a long thing. You look at where most of the matches are after you shift. You do this shift of the encrypted text, and then you look at what has the most matches. On the low ones, it's 3, so we probably know the key like this 3. And then it does literary analysis and tries to find an E and A because they're the most common letters, and it spits back out our key Tom. So moving on, here's a little diagram too showing kind of the key wrapping around and some ciphertext. And then there's also the one-time pad, which I'm not going to show right now, but it's the only completely secure cryptography method. It's just like Vigenère, but if the key was just random and longer than the actual message, and it is the only cryptographic algorithm that's impossible to break because every plain text is the same uh, likelihood of coming out of the encrypted text. Next, we have AES, which is an advanced encryption algorithm. It does a bunch of different things, which I'll show you. I did not program full AES because it's insane. It's like several hundred lines long. So I made a simplified version of AES. Uh, so we put in a word that is a certain amount of bits, 2-bit key, and how many rounds we want to do. So I'll show you this. This first step, it's a lookup table. So it turns this into a graph. And then there's a lookup table, which is right here. It breaks it into words and then looks up. And it does kind of a shift that way. Then it flips the bottom. And then it flips the top. And then it does an XOR. And this is 2 rounds, so it did that twice. And then it decrypts. It does the XOR, and then it flips the top and the bottom, and it flips the bottoms, and then it does another lookup. Then we're on to round 2, and that is the string we put in originally. And then moving right along, we have RSA, which uses a bunch of math that has to do with exponentiation and like powers modular prime. Here, I'll show you some of the code too for AES2. So this is a lookup table. That's the inverse. That's the XOR function. This breaks things up into subbytes. And then this is the shift and the flip. And then we have just the reverse of all those. So then to encrypt, you just give it the key, and to decrypt, it does the same thing. But back to RES, it Basically, it uses this property of primes and exponentiation to let you give out a public key. So first, we make a big list of primes. It's a very simple algorithm I wrote. It literally just goes up and finds primes, and then we pick two random of them between like a limit. So then we multiply them together. That gives us our n, which is part of the public key. And then to get e, you do this thing where you find the totient function, and so e is just a random thing between 2 and the totient function that doesn't have a common denominator with the totient function, and then e is just a random int in between there. And I'm not going to pretend like I understand all of the math, but basically you pick that because of the properties of math. If you take something to the e modulo n and then to the d modulo n, they're inverses. So then we calculate the d, which again, it is just calculating the modular multiplicative inverse, I think it's called. So then to encrypt our message, we do our message to the power of e modulo n, and then to well, what actually happens is, so person A picks the e and the n, and they give it to person B. Then person B gives them the message back, and then they have this secret key D, which is the that does the decryption. So you take the message to the power of the encrypted message to the power of D. That actually does the reverse of taking the number to the power of E. And then we also have a factor attack that I'm going to show you. So we just do run RSA. We're just kind of picking how big we want the list of primes to be. Don't go too big because the algorithm gets really slow at the end. So what key do we want to send? About 700. That's the encrypted number. And then it decrypts it using the method. And these will change every time that you run this because it's picking random things. And then we can do a factor attack because n is public. If we can factor it, we can get P and Q. And then finding out E and D is just based off of P and Q. So we're just going to try and factor it real quick. And we get the number back. If I had more resources on my computer, we could use really big numbers for this, but I don't have that good of a computer. Okay, so moving on to my algorithm. Basically, one of the things about RSA is that it takes the people that do it a very small amount of time to decode the message, but it takes a malicious person a lot of time to decode it. So I thought, why not put a trap door? So why don't we make something that changes on a time interval? And so what I did is I set up 3 web servers on 3 ports on my computer. And what that does is they just have one-time pads, which are uncrackable, that just change at a certain time interval. And so what the cipher does is the people exchange what port they want to use using RSA, and by the time the person gets done factoring it, which we'll simulate, because again I can't run super huge stuff where the trapdoor function on factoring gets super big. By the time that happens, the random one-time pad is already changed. So let me just make sure my servers are up. And then, so these are just 3 web servers on each port. They just listen for a get request, and then they send back whatever they have. And then I have this thing called web.py that just sends. This is what sends like the random one-time pads at 5-second intervals. So we gotta start web first, And then we go to my cipher. We'll pick something not too crazy. Hello, how are you? So we can see here, it did, these two did encryption really fast, and then I just put a little sleep timer on the other guy to simulate him like taking a long time to factor, and you can see that by the time he decoded the same port, but by the time he got to it, it had already changed to a different thing. So yeah, so I really did have a lot of fun doing this project, especially making the little AES, because I really didn't have anything to base it off of. I was just kind of going off what regular AES does. Um, and yeah, so a lot of this math was over my head, and some of the implementation was tedious. And honestly, making my own cipher was kind of scary, but I really do feel like I've made something that could like possibly be used by an actual security agency or something. Because if you didn't do 3 ports, you did 1,000 ports, then someone would have to watch all of those ports all the time, and that would just be a ridiculous amount of memory. Whereas your guys just have to do one get request. You know what I mean? So I think it's actually like a really good trapdoor function that I made, and it's honestly probably one of the coolest things I've done here at Towson, because I really do think this could have some practical applications. So yeah, that's what I did. I might have a little bit of time left, so I can just show you the one-time pad, I guess, because it's the one I didn't get to, and then that'll be it. So we just pick something like howdy doody, and then I have the Gettysburg Address loaded up on to here too. So that's our pad. Just goes through each of the numbers is something crazy, and then it pops back up. Normally it's randomized. So yeah, I'll just show you. Um, yeah, so these are just get requests. And then it just runs RES and then the one-time pad algorithm. So I think I accomplished pretty much this. This was really what I was aiming for, and I got it to at least a workable state at the beginning when I was using just Node.js. I mean, it was terrible. But I'm not going to talk your ear off anymore. That's my project, and I hope you have a awesome day. And